welcome back to Math 332. Today we are going to look at section 1.5, which is given an invertible matrix A. How are you going to use the row reduction method to find its inverse? Right, so this video is going to consist of two sections. The first section is pretty straightforward. We're going to start with a computational example. And in the second section, we will want to look at the concept of elementary matrices and how are we going to use that in order to derive the method which you're going to see in the first section. All right, let's get right to it. Right, let's start with the first example. So suppose you have a matrix A, 3 by 3 matrix A. We want to find the inverse of this matrix by using nothing but row reduction. So in order to use this method, first thing you need to do is to put this matrix A into an augmented matrix like this. Basically, it means that you have to create a slightly bigger matrix, which is going to look something like that, where you're able to put the entire matrix A right here, and then you're going to put a 3 by 3 identity matrix right next to it. So once you have this augmented matrix, we are going to do the typical row reductions. The only thing that is different, I mean, it's not really different. I just want to point this thing out, just in case you don't really know that, is that this time when we do the row reductions, we are going to do the row reduction on this entire row. So this is your second row now. And similarly, this is your third row. So when you're changing your third row, you have to change not only this, but also this, okay? Right. Now, once we put the matrix into this augmented matrix form, we want to row reduce this matrices all the way to the typical RREF matrix that we want. So the procedure is the same. First thing you have to do, since we already have this as 1, is to use this 1 to kill off these two numbers. Now, by now you should know what type of row operation you need to do in order to kill off that two numbers. So these are the row operations. So you will have, this is a 0 now, and this is a 0. And also you can see that this part here will change, because when you do the row operation, you do it through the entire row like this. So this part here will change. This part here will change accordingly too. Right, so once we have this to 0, this is now a new pivot. And what we want to do is to use this pivot to kill off this number. Now, the right row operations to use is right here. So we kill off that numbers. Remember that this part here will also change, because when you do the row operation on the third row, this entire third row will change, right? So now we have that, and our procedure requires us now to, once we have this pivot, the procedure requires us to use this pivot, this number leading 1, to kill off these two numbers. So these are the right row operations to do that. And once we have this to 0, we will go back to this pivot, and then we're going to kill off this number 2 right here. And the right operations to do that is right here, as you can see. Now, this method says that if you manage, in the process of getting your RREF matrix, if you manage to turn this part here, instead of A, you turn it all the way to I. If you manage to do that, whatever you have right here, that will be your A inverse. As simple as that. Okay? So let me say that again. You put the whole thing into the augmented matrix, and you started to do row reductions. And if you manage to reduce the A, the whole thing here, into an identity matrix, then whatever you have here, that will be your A inverse. All right. Now, first questions that you might have is, what happens if I cannot change this? I cannot change this all the ways to identity matrix. What happens when we do the row operations? I have like a 0 right here. Now, if that happens, which means that when you cannot obtain an identity matrix right here, then you will simply say A inverse does not exist. As simple as that. Well, okay. So this method can also be used to determine whether or not a matrix is invertible or it is not invertible. Well, simply put everything into this augmented matrix system, and if you do the row reductions, if you end up to having something that is not identity matrix, then the matrix A, the original matrix, is not invertible. But like in this case, if you can turn this A into identity matrix right here, okay, shown right here, then whatever you have right here, that will be your A inverse. All right, cool. Now, so because of this, it's actually pretty easy to implement this using your calculator or the web link that I shown you in class. So suppose you have a 4x4 matrix, okay, and question is find A inverse. Now, of course, this is going to be a little bit more complicated because it's 4x4. So I would not ask you to do it by hand in exam or stuff like that, but I can ask you in homework, and I say that you can use your calculator or you can use your computer. So how you do that? Now, as I mentioned in class, your computer or your calculator cannot, they don't really have the augmented matrix functions. So in order to perform this procedure, you just kind of have to get rid of the line and then add back the line when you finish doing the row reductions. So in order to implement these methods to this 4x4 matrix, well, you just have to create a matrix which has 4 rows and then 8 different columns. Okay, so part here. So right here, you will put the 4x4 matrix, and then here you will put the 4x4 identity matrix. 4x4 identity matrix will look like this. And then you ask the computer or your calculator to do the row reductions. Okay, it's complicated. Apparently, they are total of 13 row operations required. So it doesn't really matter because you're using your calculator or your computer. So you can see that we managed to turn our matrix A to identity matrix, which is good, which means that this right here will be the A inverse. As simple as that. Okay, now this is the procedures on computing A inverse, and as I said, if you cannot turn this into the identity matrix, then you just simply say that A inverse does not exist. Okay, now why this method works? How can we find the A inverse by simply doing row reductions? If you have these questions, then you should definitely check out the second section. Actually, you have to check out the second sections because in your homework, they ask you a lot of questions about elementary row operations and the elementary matrices. And also in the exam on Tuesday, I am going to ask you questions on elementary matrices as well. So I don't think it's up to you. I'm sorry. You have to continue to watch this video. Okay. All right. Now, so this is the second section, which we want to talk about the concept of elementary matrices. Well, the definition is pretty straightforward. The definition says that if you start with an identity matrix, which is like this, let's say we generally look at a 3x3 case, the rest is the same. Okay, so if you start with an identity matrix, okay, and if you do one row operation, key point is one row operation. If you do one row operations on your identity matrix, say for example, we take the second row and we change the second row, changing it by subtracting 2 times the first row. So this is one operations. This is one legit row operations. Then you get this matrix. Now this matrix, because you obtain this matrix from doing one row operations from the identity matrix, so this matrix right here is the elementary matrix. That's the definition. And sometimes we write our elementary matrices using these notations to basically spell out everything you need to know about that one operation that you did. So we sometimes write like this to indicate what happens, like how do you get this elementary matrix. This elementary matrix is obtained by doing this one single row operations on our identity matrix I. That's the definition, as simple as that. So in the exam, or in the test on Tuesday, I might give you a whole bunch of matrices and ask you which one of it is an elementary matrix. If that's the case, you just have to figure out which one of it can be obtained by doing one operation. If you have to do 2 operations to get to that matrix, that is not an elementary matrix. Okay, now, so we have the definitions. That's pretty straightforward. Now, we want to look at what happens if you take this elementary matrix and if you left multiply it with A. Left multiply means that you take this matrix and you multiply it with matrix A, but multiply it to the left of your matrix A. So for example, like this. Now, you can do the typical matrix multiplications to figure out this give you this give you this give you this. But you remember in the first video and also in the first test, there is something that we call the row pictures of matrix multiplications. Row pictures, okay? Which is like, if you remember, you should, this is one of the things that I said is very important, which is that if you have a row of a matrix, you have a row, okay? Row vectors multiply a matrix like this, assuming the size are compatible. Then what happened is that they are basically like taking, so for example, let's look at this, okay? So for example, you look at this row with this matrix. So the row picture says that what happens is that you take the 1, multiply the entire row, plus the 0, multiply the entire row, which is nothing, plus 0, multiplying the entire row. So the end result of taking this row vector, so the end result of taking this row vectors multiplied with this matrix, it gave you this, okay? It got you the first row. Okay, now the second row, if you take the second row, multiply this matrix, what happens is that they are going to take the -2, multiply this entire row with -2, and then plus 1, multiply this row, and then plus 0, multiply this, which means that we're not going to care about this third row. So the end result is that you are taking the -2 of the entire first row plus the second row. So this is what you get. See, this is what you get. So this is so-called a row picture. Remember that there's also a column pictures. There's a column picture which have a matrix and then multiply a column, and it turns out that this is like give you the linear combination of all their columns. So I said it many times that you need to be able to see this kind of thing, because now, as you can see, we can apply it, and you can see pretty easily that this multiply this give you this. Okay, now before we move on, just want to point out one very important observation. That observations is this. Now, how do you get this elementary matrix? Well, we get this by doing this row operation on I, right? Let me say that again. How do we get this matrix, this elementary matrix? We get this by doing this row operation on I. Now, if you take this matrix and you multiply A, what is the consequences of it? What do you get by taking this elementary matrix multiply A? Well, what you get is basically you are performing this same operations which you perform on I, but now you're not performing on I, you perform it on A. So this matrix multiply A is equivalent to doing this row operations on your matrix A. Is that clear? I can't really hear you anyway. So, all right. So let me say that one more time. Okay. So if you take this matrix, you multiply this, it is the same as if you are doing a row operation, this row operations on A. That's that. Okay, so this is a very critical, important information, which means that if you want to do row operations, instead of just doing row operation, you can also hit it with a matrix. That matrix is the elementary matrix. It's equivalent to doing like one row operations. Okay. Now, hopefully you still remember that there are 3 legit row operations. One of it is row operation. This is a legit row operation. You can do that. Another legit row operations is to multiply or divide a row, entire row with a number, which is like, for example, here, if you are taking the first row, multiply the entire first row by 1/2, which gives you this. So you take your identity matrix, you multiply that, you're doing this row operation, which is multiplying the first row by 1/2, then you get this. By definition, this will be an elementary matrix because it is obtained from doing one row operation on our identity matrix, right? So that's the notations to indicate. We don't really, I mean, we sometimes write like this to indicate, if we have time, to indicate what type of row operation we did on I. And if you multiply this, again, using the column picture, the row pictures, you should be able to see pretty easily that this, multiply this matrix, give you this. All right, that's pretty straightforward. And even more straightforward is this guy, multiply this. Well, everything is gone except the second row, which is right here, right? And finally, if this multiply with this, well, everything is gone. No first row, no second row. You only get the third row, which is this. And do you see that same observations that we have made last time, which is if you get this elementary matrix, if you get this elementary matrix by doing this row operation on I, then if you take this multiply A, then you are basically doing this row operations on A right here, as you can see, right? So finally, there is one more row operation, legit row operation, which is interchanging row. You can interchange row. That's a legit row operations. So for example, in this case, I take identity matrix. I interchange my second row and the third row. So I interchange my second row and the third row. So I have this, I got this. And this, by definitions, is an elementary matrix because I obtained this matrix from doing one row operation on I. And that's my notation. And again, same thing as before. If you hit this matrix with A through these multiplications, you can see the consequences of doing that is interchanging your second row and third row of the original matrix A. So that's what you get. So let me say it one more time. If you obtain an elementary matrix by doing this row operation on I, then if you take this matrix multiply with A, it is the same as if you are doing this row operations on A. Okay, cool. Now, next question is that whether or not elementary matrices are all invertible. And the answer is, as you can see, the answer is yes, all elementary matrices are invertible. And in fact, we can find what are their inverse pretty easily by just undo the row operation you did on I. So for example, so this guy right here is right here, same example as before. So in order to undo these operations, I'm going to hit it with this matrix. So this matrix here will preserve the first row because I'm not going to change the first row. In order to get identity matrix, I need the 1, 0, 0. I already have that. But in order to make this thing here to be 0, 1, 1, I need to get rid of negative 2. And the way to get rid of negative 2 is, see that? See that? Okay. So I'm going to take 2 times the first row, 2 times the first row, add the second row. So I'm going to, by doing that, I can undo the negative 2. See that? And I'm not going to change the third row. I already have the third row. So I'm hitting it third row with this matrix to get this. So you can see, and this is always true in general, that this kind of row operations, you have an elementary matrix, elementary matrix by doing this row operation. The inverse is this. Okay, and we don't really have to check the right multiplication on the right because we have that powerful lemma. We only need to do one so that we can, just look at the row pictures. Because if you hit this matrix to the right, you want to think of it from the right hand side, you will have to use the column picture. Okay, column pictures. If you don't know what the hell I'm talking, if you don't know what I'm talking about, well, try to review the things that we have for test 1. Okay, if you're doing things here, that will be something to do with column. But if you want to look at the row pictures, you have to look at this side. Cool. Now, same thing as here too. In order to reverse these operations, so in order to get rid of this, last time you divide 2, now I'm going to force you by multiplying 2 so that we can get 1. Pretty straightforward. That's the inverse. Pretty easy. So elementary matrices of this type is invertible, and this is the inverse. Same thing here. How about interchanging row? Well, same thing, easy. This is E2, interchange 3, second row change to the third row. If you hit the same matrix right here, see, it's the same matrix. Okay, it's the same matrix. So if you look at right here, okay, preserving this first one because I'm not going to do anything on that. So it's 1, 0, 0. Now, so this one right here now, I am going to pick up the second row, the third row. I'm going to place it on the second row. So it's right here. Okay, and then here I am going to place my second row, which is this, okay, and put it in my third row, which is this. So in fact, as you can see, for the elementary matrix obtained by interchanging row, the inverse is exactly that same matrix, because if you change it once and then you change it back, you get the original identity matrix, right? Straightforward. So now you can see that, yeah, you're right, all the elementary matrices are in fact invertible. And not only invertible, we actually know exactly what their inverse is by just simply, give it a little bit of thought just by looking at this row picture. Now, obviously, this is not a mathematical proof because we didn't do this in general. These are our example. So this is not really a proof in general, but I think you can see if we have like general n by n, it's the same process. It's just that it's harder to write because it's like A11, A12, but the concept is the same. So I think you pretty much I can convince you. And also this number is like 1/2, but if it is like 1/a, like in general numbers, you know that you just take the reciprocal, and then it will work. So even though this is not a general proof, but I mean, if it's required, you should be able to prove this. Okay. So yeah, I'm just satisfied with this. You don't really have to prove all this thing in general. Okay. But I'm assuming that you can see why now that they are invertible and that's inverse. Just simply looking at the row operations. Okay. The matrix multiplications using the row pictures. Cool. Now, we are almost there. Just want to remind you of two important facts. You kind of seen this before. Remember a theorem, we'll have to start with a hypothesis and then state the conclusions. The hypothesis here is that these two matrices are invertible, okay? And if they are invertible, then their inverse, the product, is also invertible, and the inverse is given by this. Actually, I mean, it's also easy to extend this to like 3 or 4 or 5 on general n matrices. So suppose A, B, C are all invertible. Key point, they are all invertible, otherwise it will not work. Then the product also invertible, and in fact the inverse, as you can see, is C inverse, B inverse, A inverse. You kind of have to flip the order. Why is that so? You can kind of prove it pretty easily using definitions. So that's the first thing. Second thing is that should be obvious, but I didn't really say in class, which is like if you have a matrix A, okay, this matrix A is invertible. This is invertible. A invertible. A is invertible. So this is the inverse, right? The inverse. Now the question is this new matrix, okay, which is the inverse of A. Is it also invertible? Which means that do we have this? And the answer is yes. This guy right here is also invertible, and the inverse is actually nothing but A. Okay, A inverse is A. Why is that? Well, actually very straightforward. From the definitions, if A is invertible, we have this relationship, right? If A is invertible, we know that there's a matrix B. If you multiply it with this A, you get I. There's a matrix B. Multiply with that, okay, you get I. And we usually don't call it B. We write B as A inverse. So we have this relationship. This relationship hold. Okay. Now, so change perspective a little bit. Now you concentrate on A. You look at A. A multiply this guy. Okay. Sorry. Now you change perspective. You look at this. This matrix multiply this. Apparently change it to I. This matrix multiply this. Apparently change it to I. So what is this matrix invertible? Is this matrix invertible? Yes. What's the inverse? Right here. That's the reason why you get this. So these are the two important facts that we're going to need in order to understand why the previous row reduction method give us the inverse of a matrix. Okay? All right. Now, we are doing it now. Okay, so it's the same matrix as the first example that you saw, and this is exactly the same notes that you have. So that's our matrix A, that's our I, okay? So remember that we started with this row operations. We changes we try to kill this number, so we have to use this row operations. So in order to get this one here, in order to get this part here, right? So what happened is you are taking an elementary matrix, actually is this elementary matrix, okay, and then hit it with A, and then you will get this. Actually, sorry, I skipped a step, so you don't get this. You will still have the 1, 0, 8, 0, 0, 1 because you only do one time. So if you do this, you will have 1, 2, 3, 0, 1, negative 3. You didn't do anything on the third row yet, so you have that. So if you hit it with A, you have this. Actually, because we do the row operation on this also, so this part here, if you do one row operation on it, that will give you like row 2 minus 2 row 1 I, and it will give you, if you give you 1, 0, 0, negative 2, 1, 0, 0, 0, 1, right? So you will get not this, but that. So just keeping track of this indices is going to be a pretty, there's a lot of work to write all this thing down. So I am not going to write all the row operations. I'm just going to denote that whole thing as E1. At one single elementary matrix, if you multiply A, you get the one that I just wrote down. But we did two row operations. So once you have this, okay, you do another row operation on this matrix. So you have E2. So you have E2, okay, E1A for this. So this part here, let me erase this. Okay, so this part here is E2, E1A. E2, E1A. E1 is the elementary matrix by performing this row operation. And then E2 is the elementary that performing this row operation. So you hit it A with these two row operations, you get this. Now, remember that we do the row operations on the entire row, including this one. So here, the identity part here will also be E2, E1I. Okay, is that clear? So you do two row operation on A. You do two row operation on A, so you get that two row operations on A. Remember that I keep saying that, right? Multiplying elementary matrices with a matrix A is the same as if you are doing those row operations. So you do two row operation on this also. Not any two row operation, but exactly the same two row operation. That's the reason why you have exactly the same E2, E1I. So this is your E2, E1A. This is your E2, E1I. Then you do row operation. On this E2, E1A, and you do the same row operation on this E2, E1I. So here you do one row operation. Let's call that elementary matrix that correspond to that row operation as E3. Let's call that E3. So you're hitting E3 with this, right? You're hitting E3 with this. You're hitting the E3 with this, because you do one row operation on this and on this. So therefore, this matrix here is E3, E2, E1A. This matrix here is E3, E2, E1I. Right? Same thing. Now you do two row operations on this. So you do this two row operation on this. You do this two row operation on this. So this is this matrix. E5, E4, E3, E2, E1A. This is E5, E4, E3, E2, E1I. Okay? Right. Finally, you still need to do one last operation to kill the number 2. So you take this matrix, which is this, and you do one row operation on this matrix, and we call that operations, E6. We call that elementary matrix associated with that one row operation as E6. So E6, E5, E4, E3, E2, E1A is this. And E6 of E5, E4, E3, E2, E1I is this. So, as you can see, this is your I. Okay? And this is your B, the matrix B. We don't know it's A inverse yet because I told you it's A inverse last time. Here, we try to prove it, right? We try to show that, yeah, this is actually the A inverse. We don't know that yet, okay? But we don't really need this one right now. We're just going to concentrate on this equation, okay? So I'm going to rewrite this as right here. As you can compare, they're exactly the same thing. There's no BS. It's exactly the same things. E6, E5, E4, E3, E2, E1. I is I. Why is it I? Because, as you can see, that's I. That's I. That's the identity matrix. Okay, we're almost there. Now, well, we want to isolate the A. So, and all of these matrices are invertible anyway. So I'm going to kill off the E6. The way you do it is multiply E6 inverse and E6 inverse. Remember though, I said it many times in class, this matrix multiplication AB is not equal to BA, so you have to be careful where do you multiply that matrix. So I multiply that matrix on the left, and then I have to multiply the matrix on the left of that equation also. So I have that. So E6 is gone. Using the same methods, I'm going to kill off the E5 by multiplying E5 inverse. Okay, and then I'm going to kill off the E4 by multiplying E4 inverse across. And then I'm going to kill off E3 by multiplying E3 inverse across. And I want to kill off E2 by multiplying E2 inverse across. Always to the left, okay? Because I'm multiplying left. So I multiply left. Okay. Now, finally, I want to kill off E1. So I multiply E1 inverse on the left, 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 left. Okay, remember that you cannot say, oh, I don't have space, so I'm multiplying here. No, 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 no. Okay, no way. No, no, no. Okay, cool. So, okay, so we have A is the E1 inverse, E2 inverse, E3 inverse, and all that. Okay, the product of all these inverses of the elementary matrices. Now, these are obviously invertible matrix, and we know they're inverse. The inverse of this is like E1. They are all invertible. These are all invertible, including identity matrix, obviously also invertible. So A is a product of all the invertible matrices, so A also invertible. A is also invertible because they are the product of invertible matrices. So let's figure out what's the inverse. So misprint, there's supposed to be an inverse right here. So we figured out what's the inverse, so we find this inverse. Remember the theorem that say that AB inverse is B inverse C A inverse? So now if you invert this, you have to take the order, invert it. I will be from here, change to here. I inverse is I. And then E6 inverse, which is E6. E5 inverse is here. And all the way you will get this. I, and then the product of E6, E5, E4, E3, E2, E1. And because I is identity matrix, this product is the same as this product. It's also the same as this product. I is like 1, right? So you can multiply 1 anywhere, and you still get that. Now, so right here, you will see that A inverse is the product of all these elementary matrices in this order. 6, 5, 4, 3, 2, 1. Why is this important? Because if you look back, this thing right here, you look back, this thing right here, that is your E6, E5, E4, E3, E2, E1I. That thing. See that? That thing, this thing is E6, E5, E4, E3, E1I. And what is E6, E5, E4, E3, E1I? That's the A inverse. So that thing that you found at the end, that's the A inverse. That's the reason why these row reduction methods work. Because when you do this row reduction method, that thing here is the inverse. Okay, I'm making this video for the 3rd time now, so I just want to get this over with. And yeah, so yeah, I make a lot of mistakes last time. So yeah, apparently it take 3 hours to make this video. Anyway, so we're done. We know how to find inverse. We have the example from before. We have a computational example. So in the test on Tuesday, you're going to do one. I promise you it's a simple one, 3 by 3. Numbers are nice. You won't get into a lot of trouble because you cannot use calculator for that one. You kind of have to know what elementary matrices are and what are the effect of multiplying this, like all the visual effects, like how elementary matrices work, what are elementary matrices. So you also have a little bit of questions like that. And that's it. That's the things that you need to be responsible for for the section 1.5, and these are the material that you need to know, and you will have questions like that on the test on Tuesday. All right, good luck, and have a good weekend. Stay warm, apparently. All right, bye.